Okay, greetings, aspiring scientists. Thank you for joining me today. I hope you're doing well. So today will be my lecture on the mole, a very important idea for IB chemistry and all chemistry in general. Absolutely critical core idea where if you can't do this, you can't do many of the other topics. So let's get right into it. We'll go to my slides. So we're now in structure 1.4. We'll start with 1.4.1. This is counting particles by mass, the mole. So really we have to define what this is. And you might have heard this before, you might know what it is, some of you, but this is not really a word that we use in everyday language other than to mean a small rodent that might be a pest in your garden. I'm not sure if that's what they were thinking when they named this chemical idea. Nonetheless, they have the same name, and we're going to define the science version of mole today. So first we need to define the Dalton. I've actually already defined the atomic mass unit in some of my previous videos, and the Dalton is actually just the same as an atomic mass unit, but I want to go through its meaning and history a little bit. So this is a unit of measurement. Scientists needed to define an atomic mass unit. It's just very difficult to work with like 10 to the minus 31 kilograms with everything. So we want to define one unit that has something to do with atoms or molecules, small particles. So the scientist John Dalton, if you watched my atomic structure video, you'll realize he was one of the first proponents or people who introduced an atomic theory. Same guy here. So he proposed that we use the mass of the lightest element as a kind of base unit where we can compare everything to that lightest element. And that was a great idea. Turns out the lightest element is hydrogen, and it is just one proton, so that would be a great unit to use as our base and just call it one atomic mass unit. However, hydrogen is dangerous and difficult to work with, especially in the 1700s or whenever this happened. So scientists really needed to actually study the element which we're going to base our unit of atomic calculations and molecules on. So it turns out carbon is much easier to work with, so there's also very abundant amount of carbon isotope number 12, very stable, very common. So scientists decided maybe we should use that instead. We still want to use one proton in there, but we're going to take 1/12 the mass of a carbon-12 atom instead of one hydrogen atom. 1/12 the mass of a carbon-12 atom should still be one proton, but it turns out that protons have actually a little bit different mass in different nuclei, in different environments, which is kind of surprising, but whether it's the proton themselves or something about the atom, as you add more atoms or more protons and neutrons together in the nucleus, there's a thing called binding energy which appears as extra mass. So if you just divide the carbon atom by 12, it doesn't exactly match one proton in a hydrogen atom. That's what I'm trying to say anyway. You'll learn more about that if you take IB physics class. So now we're going to use 1/12 the carbon-12 atom. That is 1 Dalton, so a carbon-12 atom is exactly 12 Daltons by definition, 12.000 going forever. And a Dalton is the same as an atomic mass unit. You'll see that used sometimes, and also the symbol U is just the short version of that. So you can see my picture on the right, that's a carbon-12 atom, 6 protons, 6 neutrons, 6 electrons. We're taking 1/12 that mass as a base unit. All right, then we can move on to moles because it's directly related to that idea of the Dalton. So in the early 1800s, Amedeo Avogadro realized that comparing mass ratios was not suitable for most reactions. So you might remember that Dalton did like an experiment with water. He found, what was it? I think some mass of oxygen plus some mass of hydrogen always makes the same mass of water. And, that works after you realize it, after you measure it. You can predict that that will always happen again and again for water. But we want to be able to predict like new reactions that we don't know yet. and we want to predict with more sort of accuracy and certainty how much reactants we're going to need and how many products are going to form. And that can't really be done easily with just mass ratios. So instead, rather, it is the ratio of the number of particles that is needed. So right on the fundamental level of the reaction, it's not the masses really that matter. It's how many particles come together to react. That's what we need. It was impossible to count the number of atoms in a sample, though. You can imagine in the 1700s or the 1800s, it's very difficult. We can't even do that now that easily, to count a specific number of atoms. But after we've defined the Dalton, Avogadro and probably some others had the idea, okay, so there must be a number of particles that would have an equal mass in gram units to the particle's weight in Daltons. All right, I'll repeat that. It's really important to understand. There must be a specific number of particles that would have an equal mass in grams to the particle's weight or mass in Daltons. Okay, so you can imagine I have some hydrogen atoms. They have 1.01 Dalton atomic mass, right? I can keep putting more and more and more together, and he's asking, how many do I have to put together until I get 1.01 grams? I want a gram number that's equal to its Dalton mass of one particle. All right, so you keep doing that and doing that and doing that. And he was able to basically calculate what this number would be for any particle. It doesn't matter what it is. It could be hydrogen, carbon, could be ions, could be molecules, could be bananas, whatever. So what is a mole? The number that he was searching for there was calculated to be 6.02 times 10 to the 23 particles. And this is now written as Na, Avogadro's number, N subscript A. Sometimes L, but we're going to use Na in my classes and in the IB, I think, most of the time. So this is Avogadro's number. It's in the data book in the constants section. Now this number is extremely useful, as scientists can now determine how many particles are in a sample, any certain mass for a sample of known composition. So if you know you're dealing with water, or 50% water, 50% NaCl, or if you know you're dealing with nitrogen gas, or if you know the chemical formula really of what you're dealing with, you can find the number of moles, which is a representation of the number of particles. So you might ask how, and we're going to get into that today. So 1 mole of anything contains 6.02 times 10 to the 23. People often compare this to like a dozen or a few, right? A dozen is 12 of anything, right? Well, a mole is just 6.02 times 10 to the 23 of anything. It's a massive number, but it's just like saying a dozen of something. But as soon as we defined a Dalton to be 1/12 the mass of a carbon-12 atom, this number became set. It's directly linked to whatever we have as our base unit for particles. So an equation then comes out of this, fairly simple equation. Number of objects or particles, big N, equals number of moles, little n in units of moles, multiplied by Avogadro's number, 6.02 times 10 to the 23, a constant number. And the units of that are usually mole to the power of -1, meaning per mole, but it really means objects or particles per mole. We just usually understand that we're talking about atoms, so atoms are molecules, so we just ignore the objects part of that. So what does 1 mole look like? I like this picture I got from Science Res EDCPEDUC website. It's just a good visualization of what 1 mole of a bunch of solids look like. So generally it's like about a regular beaker's worth of stuff, right? You could have sugar, sulfur, copper sulfate, pentahydrate. So the size of this, or the volume, really depends on a lot of things. It depends on the molecular mass, or the atomic mass. It depends on the density as well. That's why I think copper is very small, but probably very heavy in this picture. Sucrose, however, is probably not very dense, it's just sugar, but the molecular formula of sucrose is very large. I think C12H22O11 or something. Very large molecular weight, and that means there's going to be a large mass to create 1 mole. All right. Gases will be much bigger volume than this because they have extremely low density, and liquids, you know, somewhere around this. Okay, I do apologize, this is my second time trying to record this video, so I've already completed some of these practice questions, but calculate the amount of tin, SN, in moles and millimoles in a sample containing 2.4 times 10 to the 22 atoms of this element. So you're going to use the equation I showed on the previous slide, but you're going to rearrange it for little n. So the equation was big N equals little n times Na. So rearrange this, divide both sides by Na. We'll get n, the number of moles, equals big N, the number of particles, divided by Avogadro's number, Na. So you'll notice that tin itself and the element Sn has nothing to do with this calculation. You don't have to go look it up on the periodic table to answer this. So 2.4 times 10 to the 22 is less than 6.02 times 10 to the 23. This means this cannot be 1 mole. It has to be quite a bit less than that. And you'll divide big N by Na. You'll get 0.040 moles of tin in this situation. Okay, and then to answer this in millimoles, we would just multiply that by 1,000. So this will end up being 40 with a decimal place after the 0 to show our 2 significant figures, millimoles. Okay, something like that. So let's move on. More examples. What else do we have? The number of atoms in 2.5 moles of neon gas. So again, the name of this gas is kind of a trap. You don't need this at all. You don't have to look up this on the periodic table. You can just use the formula, number of particles, which is atoms in this case, equals number of moles times Avogadro's number, Na. So we have 2.5 moles. We're going to multiply that by 6.02 times 10 to the 23 atoms per mole. We'll get 1.5 times 10 to the 24 atoms. Okay, the number of molecules in 0.50 moles of ammonia, NH3. This one I will write again here. So we want number of molecules again, that's big N. This will equal little n times Na. Equals 0.50 mole times 6.02 times 10 to the 23 per mole, and we'll get exactly half Avogadro's number. We should anyway. So that ends up being 3.0, we'll cut this to 2 significant figures, times 10 to the 23. Molecules. Part A was atoms. Sorry, very difficult to write with this pen. Then we can move on to part C. And that is the number of atoms in 0.50 moles of ammonia. So B and C look very similar. What's the difference? Well, B asks for molecules, C asks for atoms. So ammonia is one molecule itself, but how many atoms are in there? N and 3 H's, that's 4. So you just need to multiply the answer to B by 4. Really, it's a ratio of 4 atoms per 1 molecule. So this way, our units of molecules will cancel out. We'll be left with units of atoms. And this is about 1.2 times 10 to the 24 atoms. All right, so you're often going to have to check the ratio between, multiple different chemical formula or atoms within a formula. Let's move on. So that's the end of 1.4.1. We're going to move on to 1.4.2 and 3. This is relative molecular mass and molar mass. So relative atomic or molecular mass, A subscript R or M subscript R. We've actually already talked about relative atomic mass in my isotopes video, but we'll review this here. Relative atomic or molecular mass represents how heavy or how massive the atom of a particular element is compared to a standard. Scientists have chosen the standard. That's what I introduced in the first slide today. We chose it to be carbon-12, and specifically 1/12 the mass of a single carbon-12 atom, which is about the mass of one proton in that context. By definition, this sets the weight of carbon-12 specifically to 12.00000 going forever, and that's relative mass units, AMU or Daltons. And this is unitless. So actually, Daltons and AMU are a unitless quantity. They come from a fraction, really, a ratio of the mass of something divided by the mass of 1/12 the carbon-12 atom. This would be kilograms divided by kilograms, which cancels out to 1. But we just label it with atomic mass units. So the formula for any atom's atomic mass unit mass is then AR for atoms, or MR for molecules, equals mass of that atom or molecule divided by mass of 1/12 of a carbon-12 atom. So you do need to know how to define AR and moles in this way related to the carbon-12 atoms. So I would definitely make sure you understand this. If you didn't particularly understand my explanation here, read a textbook or check an online resource. Sometimes having a second explanation can help you get your mind around this. All right, next brings us to, I think, one of the most important slides in the whole course. So really important to know everything on this slide. So starting in the top left, this is just what I wrote on the previous slide. It's a reminder of how we get MR and AR, the relative atomic or molecular masses. But we don't actually do that calculation very often because all the elements' relative atomic mass is written on the periodic table. We can just go look at it there. But what do we do? Well, let's look at the right side. So I have 3 containers here: iron, Fe, lithium bromide, LiBr, and water, H2O. So all of them are in these 3 separate containers. They don't necessarily have the same volume, and they don't have the same mass. Okay, the iron has 55.85 grams, lithium bromide has 86.85 grams, H2O has 18.02 grams. Okay, now what you'll notice though is on the left, well, in the middle of this slide really, all of these containers have the exact same amount of particles. I mean atoms or molecules. For iron, there's just atoms, so there's 6.02 times 10 to the 23 atoms in there. LiBr is a compound, H2O is also a compound molecule, so those particles refer to really molecules, or maybe like a crystal lattice unit for LIBR. We'll learn about that later, but don't worry. So it's just, this represents particles, a particle of this particular chemical formula. All right, so all these containers have the same number of particles but different masses, and that's what's going to happen very often. And you'll notice that these masses are exactly what you would find on the periodic table for the molecular weight of these elements. So iron is just itself. Its number for mass on the periodic table is exactly 55.85, I think it should be. Then if you took lithium mass plus Br mass on the periodic table, you would get 86.85. If you took 2 hydrogens and 1 oxygen from the periodic table, their masses, and add them together, you would get 18.02. So it must be true that 6.02 times 10 to the 23 particles, the mass of that for any element or compound is equal to its mass in Daltons, or atomic mass units, what you would get from the periodic table. That's the whole idea of the mole. And so this number, some number of grams for the mass of these containers, or what's in these containers, is their molecular weight or atomic weight, but it's also something else that we're going to call big M on the bottom right here. So this is molar mass. It's just the mass in grams of 1 mole, and it has exactly the same size of number as the element or compound's atomic mass or molecular mass from the periodic table. Okay, that was a lot to follow, but please go back and rewatch what I just said if you didn't follow it. It's really important, and we'll get into why this is useful. So on the left side then, in the middle, amount of substance has the unit moles, MOL, and the symbol little n. There then exists an equation, little n equals m over big M. That's mass divided by molar mass. Molar mass is what I just defined on the right side of this slide, the mass of 1 mole of that compound. But this is extremely useful. It means we can get the number of moles of anything if we know its mass and we know basically what it is, its chemical formula, because we can just go to the periodic table and check what its molecular mass would be. All right, so with these relationships, we can transfer between a lot of things. We can go between number of particles to number of moles to mass and all the way back with some specific mathematical operations. So to go from number of particles to number of moles, you would divide by Avogadro's number Na, right? That makes sense. If we had exactly 6.02 times 10 to the 23 of something, we would have 1 mole. If we had like 12.04, we would have 2 moles. If we had 3.01, we would have a half a mole. That's basically just what this is saying. All right, and then if you wanted to go from number of moles back to number of particles, you multiply by Avogadro's number instead. All right, if you want to go from number of moles, little n, to mass, you're going to multiply your number of moles by the molar mass. Remember, the molar mass is a certain number of grams per, grams per mole. So if you multiply moles by grams per mole, you'll get the mass of whatever you're talking about. But more often, we're going to start by doing the opposite of that. We're going to take a mass and we want to know how many moles it is. If you just go measure like some grams on a scale in your laboratory, you want to know how many moles you've got to predict any chemical reactions you're doing. So you would then divide by the molar mass. Okay, dividing by the molar mass, you'll have grams divided by grams per mole, and you'll flip that grams per mole and multiply by mole per gram then. Then the grams will cancel out to 1, you'll be left with units of moles. So hugely important things on this slide, hugely important equations, but it's not enough just to listen to me talk. You've got to actually try some questions, which we can do here. I just want to talk about how this is linked to isotopes as well. So if you watched my atomic structure video, you'll know the first time I talked about relative atomic mass was on this slide. So I introduced, there's 3 isotopes of carbon, 12, 13, and 14. They all have different relative abundances. You can use a weighted average calculation to calculate what we would predict to measure for any random sample on Earth. And that relative atomic mass comes out to 12.0107. So the number on the periodic table is not exactly 12.000 like the carbon-12 atom's mass is. Rather, it's a little higher because there are contributions from carbon-13 and 14, mostly 13. Okay, I just wanted to mention that. Now, what if you want to calculate the relative molecular mass of a large compound? You need to just add up together everything that's in there. So here's a complicated example, magnesium sulfate heptahydrate. The whole formula of that is MgSO4 7H2O, and that 7 is multiplied by the whole H2O formula. It's kind of hard to follow if you've never seen that before, but this is fairly common in IB exams as well, so you should learn this notation of hydrate salts. So we have one magnesium. Its relative atomic mass is 24.31. We have one of that. We have one sulfur, 32.07. We have 4 oxygens in the first part of the formula. They are 16 atomic mass units each, so altogether they are 64 atomic mass units. Then hydrogen, we have 14. That's 7 times 2 in the H2O, and their combined mass will be 14.14. Then oxygen, we have 7 from 7H2O in the second half. That's 112 atomic mass units. Okay, so when you add all those together, you'll get MR is 247.15. So that's the relative molecular weight or molecular mass. Weight and mass we can use interchangeably, but that's relative molecular weight of magnesium sulfate heptahydrate. And one last thing that I think is very useful to do is to check the mole ratio of everything within this formula. So the ratio of Mg to S to H2O is 1 to 1 to 14 to 11. I'm adding the 2 oxygen sides together. That's 4 plus 7. So it's very often you'll need to compare ratios inside a formula like this, so I recommend being familiar with how to do this. All right, moving on. Again, I've already done this practice example, so sorry about that, but I think it's not too difficult. Calculate MR for a molecule of acetone, C3H6O. So what you would do would just multiply carbon relative atomic mass by 3, it's 12.01, plus 6 times relative atomic mass of hydrogen, 1.01, plus 1 times relative atomic mass of oxygen, 16. And you'll get 58.09. And unitless, it's not asking for the molar mass, it's asking for the relative molecular mass, so we don't write any units here. But the molar mass would be the exact same number here, just units of grams per mole. All right, more practice. Calculate MR for ammonia, sulfuric acid, and sodium sulfate decahydrate. Okay, so I'm not going to do the whole calculation for these. You guys, if you want, you should pause the video, try it yourself. Then if you've tried, I'll move on. So I get the answer 17.04 for A, 98.09 for B, and 322.25 for C. So hopefully you got the same. Again, I'm using the IB data book to add up all these masses from the periodic table. All right, moving on. Another example, sugar is almost entirely sucrose. Sucrose is an organic compound with the molecular formula C12H22O11. Calculate the molar mass of sucrose, so we would add up the mass of each individual atom in there. B, the amount of moles of sucrose in 1 cube of 2.80 grams, so we would use the formula in the top right corner here. And C, the number of oxygen atoms in 1 cube of sugar, and 1 cube weighs 2.8 grams. Okay, so to answer this, I'll go in detail and I'll go to the whiteboard. Okay, so first we need the molecular mass of sucrose. It's going to be 12 times relative atomic mass of carbon. 12 times 12.01. We would add that, add that with hydrogen, which is 22, multiplied by its relative atomic mass, 1.01. And then we'd add oxygen, 11 times that, 16.00. And you will get hopefully 342.34 atomic mass units. So this is AMU, and the molar mass of sucrose, which is C12H11, H22O11, is the same number with units of gram per mole. Okay, that's always true. Whatever you calculate to be the relative molecular mass will be that compound's molar mass. Okay, what was B then? B says a cube is 2.8 grams, and how many moles will that be? So we want to go back to our previous equation. Number of moles equals mass over molar mass. And we will use 2.8 grams, 2.80, divided by the number we just calculated, 300, I don't like that, 342.34 gram per mole. So our grams units will cancel out, and we will get, just let me put that in my calculator quickly to double check. Zero point 0.00818 moles, or 8.18 millimoles. I think that would also be okay. So just highlight my answers here. And part C asks how many oxygen atoms are in this cube of sugar that's 2.8 grams. Well, what's the ratio of C12H22O11 to O itself? That ratio is 1 molecule to 11 atoms of O. So all I need to do is multiply my moles of sucrose by 11 to generate my moles of oxygen. So moles, N of oxygen instead this time, equals this ratio of 11 over 1 multiplied by 0.00818 moles. So that will come out to 0.090. Really, it's 0.089969 and so on. So I'll keep that in my calculator. All right, this is also moles. So we haven't answered the question yet. The question asks how many atoms were there. But if we want to go from moles to a type of particles, we can multiply by Avogadro's number. Big N equals little n times Na. So for oxygen atoms, this will be 0.090 moles times 6.02 times 10 to the 23 per mole. Kind of out of space here. Okay. So what does that come out to? This is 5.42, 3 significant figures times 10 to the 22 atoms of oxygen, specifically. That's what the question was asking for. And I think that's the way to do this, best way. Okay, let's go back to slides. All right, what else? So there's more practice here. You can calculate the amount of moles in a bunch of different masses. So some grams of aluminum, phosphine, pH3, calcium oxide, CaO. Then you can also calculate the mass of a bunch of moles of stuff: N2 gas, H2O2, hydrogen peroxide, and sucrose. If you're resourceful, you might just use my answer from the previous slide to get you started on that. So I will provide the answers to these just in case. So if you don't want to see them, don't look yet. Coming in 3, 2, 1. Okay, these are my answers. Hopefully you get the same, and we do have to consider significant figures. So some of these answers have 4 sig figs, some 3, some 2. But I think we have to match to the information we get from the question. Can't have more significant figures than that. Okay, then that will bring us to the end of this video and this topic. Next time we'll look at something called the empirical formula versus molecular formula, but very much related to these moles and mole ratios. All right, hope you learned something. Thanks for listening. See you next time.